So continuing in our series of videos here on the scientific method and how it's applied in economics, we're now going to consider the opposite case of the previous video. We want to consider why we need models, why we can't only rely on data. And so we've hinted at what some of these reasons are in previous videos, but I'd like to dive into those. And before I do, obviously, we'll discuss why I think learning this limitations of data is so important to your lives. So in your professional lives, you need to understand the limitations of data analysis because you are never going to have enough data to understand an entire population. If we are interested in the behavior of nursing home residents, and we want to collect data on how nursing home residents behave, we aren't going to go to every single nursing home in the country. We're not going to have a census on the entire population of nursing home residents. We're going to collect a sample, and from that sample, we're going to conduct a data analysis and generalize or extrapolate out beyond that sample to make conclusions about the whole population. And if we want those conclusions to be accurate, which remember is good policy and bad policy lands you out of a job, then that is necessarily going to involve some sort of model for external validity. And we'll discuss that a little bit more towards the end of this video, but in general, a model is needed to reach the right conclusion. And when that comes to making the world a better place, if we don't consider models when making policy, we don't know if our data is generalizable, which could lead to bad policy. So similar problem, just thinking now about the world at large instead of a corporation or company. And to succeed in this class, you need to understand that there is a need, there is a role that models fill. And if we don't include that need, if we don't think about why models are important, then it's just going to seem like you are memorizing random facts, which is not conducive to learning. So when we make a policy, we want to impact one outcome or variable, but we know that we may also affect another variable. So we need to understand the relationship between those two variables. Let's say wages and unemployment, for example. So are they related? Does one cause another to change? If we change wages, if we implement a minimum wage, do we cause unemployment to change? Or if they change together at the same time, are they just correlated? And so we can understand these questions in three ways. We can do it visually with graphs and charts. We can understand it with tables, or we can understand it with equations. And in this class, we are going to use all three of these to visualize, to understand the same information. But what I'd like to do now is think about the shortcomings and really the limitations on using these three methods alone to understand data to come to conclusions about the world. So when we use graphs as a scatter plot, like these three graphs would suggest, we look for a visual relationship between a change in one variable and a change in another. So based on the graphs on this, this image here, which variables appear to be related? Can we definitively tell that the changes in one variable cause a change in another variable with these graphs? So based on these graphs, we can tell that height and weight seem to be positively related. Hair and age appear to be negatively related, and age and eye color have no relationship. However, we can't tell whether one variable causes another variable. We don't know whether being taller, having more height, causes more weight gain, or whether more weight gain causes more height. Obviously, from our own understanding, we may have an idea, but looking only at these graphs, we can't really tell. And we have a pretty good idea that an increase in age causes a decrease in hair, unless you go bald when you're 26 years old, like a certain professor who you may know did, and not the other way around. That decreasing your hair wouldn't make you younger, wouldn't cause you to live longer, but I kind of wish it would. So our causal interpretation of this graph, so not casual. Casual means laid back, relaxed. Causal, what is causing one. Our causal interpretation of this graph depends on biological models of hair loss. The main point is that we can use simple graphs to roughly determine whether there appears to be a relationship between variables, but we can't determine whether one variable causes another one strictly by looking at these graphs without a theory or a model. We can also use equations to determine whether a choice is correlated with an outcome. So instead of visual relationships, we need regression analysis, and the outputs from the analysis being the coefficients on your variables and the R squared. And so the value for the R squared will be between 0 and 1. The closer the value is to 1, the more confident we can be that the variables are related. The larger the coefficient, the greater the change in one variable that's attributable to a change in another variable. However, these values can be misleading. Without a theory or an explanation for why variables should be related, we may find a spurious correlation, a prediction that two variables are related when they really are not. And we're going to look at that in this next image and hopefully give you an activity that you will do in your free time. But before we do, I just want to point out what some of these terms that we just discussed are on this image in front of you. And this is the output from the regression analysis. We have y equals negative 2.92 multiplied by the x variable plus 4,624. And so if you remember basic graphing from high school math, you'd know that one of those is the slope, the other is the intercept. And we also have our R squared, which tells us how well that equation predicts the variation in the data. And so remember we said that R squared is going to be between 0 and 1. In this case, it's 0.7, so we're a little bit closer to 1. So it's obviously better, has more explanatory power than a similar model with an R squared of 0.6. And we look at the impact of a change in the x variable on a change in the y variable by seeing what the coefficient is in front of the x variable, in this case the negative 2.92. And so that tells us how one variable changes as the other variable changes, but once again it doesn't tell us whether there is a causal impact there. So returning now to the concept of spurious correlations, these are correlations which are just happenstance between two variables being related. There's no causal mechanism at play. And if we don't consider models and we don't at least rely on some theory for why variables are related, then we may be arriving at incorrect conclusions based on spurious correlations. So using this link, I know you can't really click on it on a video, but just typing that into your browser, explore some of the relationships between some variables which are completely unrelated and see how strong they are. So one quick example that you would find on this website is that in the first decade of the 21st century, so from 2000 to 2010, you could predict the divorce rate in the state of Maine with 99% accuracy by knowing only the per capita, which means per person, consumption of margarine. So obviously, we don't think that there's any causal relationship between these two variables. So it's a spurious correlation. We don't think that increasing more butter or margin causes the divorce rate in one particular state to go up or go down. They aren't related, and without a model, or in our case, just basic intuition of how divorce operates and how margarine operates, we know that they're not related. So this is why we need theory and models, and why only relying on data is dangerous. So spurious correlations are just examples of the logical fallacy of correlation being equal to causation. That you'll often hear that as a response to faulty data analysis, that correlation alone does not equal causation. Now, examples of this confusion are everywhere now with the politicization of the pandemic and the government response. For example, I know I've seen either in social media, online, in the news, these two claims that stronger lockdown orders cause more cases of coronavirus. So why may simple data analysis find that to be the case? Well, you can't really argue with the fact that in the US, New York City, for example, had or New York City's surrounding area had some of the highest number of cases of coronavirus, and they also had some of the strictest lockdowns. We observed the same phenomenon in Wuhan in China. However, while these two variables are correlated, cases and lockdown intensity, this is an example of reverse causality. The strict lockdowns and quarantining orders were due to the high number of cases, not the other way around. However, with a simple graph or equation, you may not be able to tell that. You wouldn't be able to tell that. On the other hand, I know I've seen claims like this: do Democratic mayors cause more coronavirus deaths? We see the highest number of coronavirus deaths in cities with Democratic mayors. So New York City, my guess would be Houston as well. However, while the data would suggest that if you ran a regression analysis with predicting the number of deaths based on only who the mayor of the city was where the deaths were experienced, you aren't going to find as many in rural Ohio or Nebraska. You're going to find them in large cities, which tend to have Democratic mayors. And so what's missing here is omitted variable bias, which leads to endogeneity. And these are words that you really won't need to know for the rest of this class, but they're the labels and examples for what problems we run into when we make causal claims, when we act as if we know something about the world based only on data and not on any model or theory. So we can't rely only on models and theory because they may not be complex enough, or they may simply be wrong. Also, we can't rely only on data because it's hard to tell whether one change in one variable causes another variable to change, and there's the possibility that correlation is spurious, completely unrelated by any mechanism, just due to chance. So we need both good theory and models and good data and empirical testing to create knowledge, to create accurate knowledge in economics. And in the next video, I'm going to wrap up this conversation of how economics is studied by discussing the difference between good research and bad research.